In this episode, we are going to solve examples on Norton's theorem. So we have our first example. It says find the current in the 8 ohm resistor using Norton's theorem. So you can see that we have a circuit with resistors, a current source, and a voltage source. We are to use Norton's theorem to find the current passing through the 8 ohm resistor. So straight away we have to know what we are looking for. We saw that in Norton's theorem, what we are interested in is our load resistance, which is given in the question as 8 ohms. We will also find the Norton's resistance, we don't know, and we will also find the Norton's current. And we will find or combine all these three in a parallel circuit. So now I will prefer to find my Norton's resistance. So finding the Rn, which is also the same way as finding the Thevenin's resistance. Now, if you are finding the Norton's resistance, you are going to open circuit every current source you have in the circuit and short circuit the voltage source. So this is how we are going to arrive. So we have a voltage source here. So it is being short circuited, and we have our resistor. This 5 ohm is over there. Now I also have my 20 ohm resistor, and the current source is open circuit, so no current is flowing through. This is the terminal to the 8 ohm resistor. So this is my diagram. This is how it is going to look like. Let me give this a proper meaning. So this is going to be the 20. So here we have our 5 ohm, we have the 20, and we have the 4. So at the terminal here, we will measure the Rn. When you look at the circuit, you can see resistors, some are in parallel and others will be in series with the other. So you can see that when you are starting, our interest is at this point, so we are going to start and move to this direction. You can see that this 5 ohm, when current is flowing through it, it is going to divide itself. So meaning the 5 ohm is parallel to the 20 ohm. So for that, I will call their effect as R prime, which is going to be parallel effect. And we know that that is going to be 5 multiplying 20 on 5 plus 20. And we can see that that is going to give us 4 ohms. Now that 4 ohms as the effect of the 5 and the 20 is going to be in series with this 4 ohm resistor. So they are going to be in series. Therefore, the Rn, the total resistance in the circuit, is going to be a series from the 4 ohm plus the 4 ohms, and that is going to give us 8 ohms as our Rn. So now we have the Norton's resistance calculated. Very simple. We have it as for 8 ohms. So we have it 8 ohms. So we are interested in the Norton's current now. And when you look at the circuit, you should find a way to make the analysis. Whatever way you find so interesting to analyze, so such that you can get the current flowing here and call it your IN, you should be able to identify the method. So here, I consider the superposition method to be very simple for me to analyze the current. You can check out for the superposition episode and look at how it is being done so that you can understand. So let's try to find our IN by using the superposition theorem. So from the superposition theorem, it gives us the advantage of, if we have a voltage and a current source, we can deactivate one and find the effects of the other one and also deactivate the other one and find the effect of the first one we deactivated. After that, we will sum the currents from the sources, each of them. You'll get to understand. So here I have a voltage source, I have a current source. So I have to deactivate one and find the effect of the other. So I'll prefer to deactivate the current source and work with the voltage source. So let me deactivate it. I'm going to use this diagram. That's for the superposition approach. So I'll deactivate it as if it does not exist. So this is how it is going to work. Now, if I deactivate this, current is going to flow, right? Yes, current is going to flow in this direction. And before I can get, let me call this current as my I. By the help of the total resistance in the circuit and the value of the voltage, I can use the Ohm's law to calculate for this current I. Is that true? Because from Ohm's law, our V is equal to IR. So my I, which is going to be V on R. So I'll get the I flowing through the circuit. And by the help of the current divider, I can also find the current going through here. So this same current will be the current flowing through the load resistor that we are interested in. I hope you understand that. That is very simple. The superposition theorem is very simple. So since we are interested in this part, we also have to short circuit this part. So I'll short circuit it, although these are the terminals that I am working with, and the current is coming this way. So this is my IN. For the first time, if the current source is deactivated, so I'll call it I prime. Are we okay? So if we have that in mind, I'm taking it one after the other so that we can understand it very well. So in order to calculate the I, since I have the value of the voltage, I will calculate for the total resistance in the circuit. And this is how it is going to be. You can see that our interest is this part, the resistance here. So we will move in this direction. This 4 ohm resistor is in parallel to this 20. Now, when you combine the two, their effect is going to be in series with this 5 ohm. Do you understand that? Because if current is flowing, it is going to split itself among this. Therefore, these two are in parallel arrangements. You can also check out for an episode on how to find the resistance of various circuits, the total resistance. So my R1, which is the total resistance of the circuit, is going to be the parallel arrangement, which is 4 by the 20. They have parallel effects. That will be 4 plus 20. That will be in series to this 5. And this is going to give us 25 on 3 ohms. So the total resistance in the circuit is 23 or 25 on 3. Now that I have the total resistance, I can also calculate for the current because I know the current I is equal to the voltage 25 divided by the resistance, which is 25 on 3, and this is going to give you 3 amperes. Is that true? So meaning the current being produced by the voltage source I is 3 amperes. Now this 3 amperes is going to flow through this 5. All of it is going to flow through this 5. As it gets to this junction, it is going to split into 2. Let's use the current divider approach to find the current that is shared between the 4 ohm and the 20 ohm. So that will give us, let's call this current is the same as the IN coming, IN prime, and we have a current also moving this way. So in order to find our IN prime first, that is going to be, we are interested in current IN prime. That is going to be, since that current is the same as the current flowing through the 4, we will use the 20 ohm as our current divider rule. So plus 20 multiplying 3, and that is going to be 2.5 amperes. So there is 2.5 amperes current flowing through the 4 ohm, and you can see that that current is the same as the Norton's current prime because we are dealing with only the voltage source. It is complicated, but please pay attention and you will understand it. Now, I have deactivated the voltage or the current source to get the effect for the IN prime. I will also work on it by deactivating the voltage, and bringing the current source. Are we okay? So let's look at a diagram where we have it deactivated and work with that. So a new page. Over here, I'm going to deactivate the voltage source and bring back the current source and make my analysis. So this is going to be let the voltage, the current source, which is the 3 amperes, act alone. Now the current source is acting alone, so the voltage source will be out. This will still be our 5 ohm. We have our 20 ohms. The current source is working. This is the superposition theory. And we have our 4 ohm here, and this will be for the terminal where we want to calculate the IN. This will be for the second time prime. So we will work with that. It is interesting working with it. So this is our 4 ohms. This is still our 3 amperes. This is 20 ohm. And this is our 5 ohms. So with this, we also have to make analysis and find the current that is going to flow through this direction, and that current will be the current that is IN prime. So let's look at how we can do that. Now, when you look at the circuit, it is giving you a clue. We have the current. So let's call this current. This is the same as I1, and you know that here I1 is the same current as that, and we have this current. I can combine the effect of these two resistors, the 5 and the 20. Are we okay? The 5 and the 20, and they will be for one circuit. So let me combine that. So we can see that the 5 is parallel to the 20 ohm, and I'll call their resistance R0. That is going to be 5 by 20 on 5 plus 20. That is going to give me 4 ohms. So meaning this is now the circuit. The effect of this 20 and this 5 is giving me 4. So this circuit can be written as this 4, this current source, the 3 amperes here, and we have this 4 ohms as that. So this is still the IN prime. Now we have this as 3 amperes, and this is 4 ohms. This is now also 4 ohms. You see that this 3 amperes is going to divide itself among the resistors. So still we can use current divider approach to also find the current. So here we are interested in the current in the 4. Fortunate for us, this is also 4. So meaning I'll call this current as my I1. So I1, which is the same as the Norton's current prime, is the same as from the current divider 4 on 4 plus 4 multiplying 3. And you can see that that is going to be 1.5 amperes. So from the superposition theorem, when we had the voltage source acting alone, we got a current. When we have the current source acting alone, we also have a current. Therefore, the total IN is going to be the effect for when the voltage source was acting alone, and that's when the current source was acting alone. And that is going to be 2.5 plus 1.5. And that is, we have a current of 4 amperes. So our IN is 4 amperes. Now we have IN to be 4. We had our load resistance to be, or the Norton's resistance to be 8 ohms, and we have the load resistance also to be 8. So with that, we can work with that. It's also 8. So we have to make them parallel to each other. So I'll call, you can draw this way, and this is my current source. So this is my IN, which is 4 amperes. This is my RN, and this is my RL. So this is going to split its current into I1 and I2. So the I2 will be the current passing through the load resistor, which is the 8 ohms, and that is going to give me 8. This is 8 ohms. This is also still 8 ohms. So 8 on 8 plus 8, multiplying the total current 4, and that is going to be 2 amperes. So from the question, the current passing through the load resistor is 2 amperes. Let's look at the next example. Example 2. It says find the current flowing through the 6 ohm resistor. So you can also see a circuit with resistors, current source, and voltage source, and we have to find the current in the 6 ohm resistor. You can pause the video and try your hands on it. So straight away we can start this. So we are using the Norton's theorem. So use the Norton's approach. So here we are interested in finding our IN. We are also interested in finding our RN and our RL. From the question, we have to find it in the 6 ohm resistor. So here we have our load resistor given. Now let's try to find our RN, the Norton's resistance. We are going to short circuit the voltage source and open circuit the current source. So meaning this is what the diagram is going to look like. We have the voltage source short circuited. I still have my 8 ohms intact, and the 3 ohms because the current source is opened. So we assume it not to be in position. I have my 3 ohms over there, and this is going to be the 6, the terminal at which we are looking for the Norton's resistance. So here we are looking for Rn. This is 8 ohms, our 8 ohms resistor, 8 ohms, and we have the 3 ohms. This is also 3 ohms. So to find the Rn, we can see that the resistor 8 and 3 are in series, and that combination is going to be parallel to the 3 ohm resistor. Therefore, our Rn is going to be, the series arrangement is 8 plus 3, parallel to the 3 ohms, and that is going to be 8 plus 3, which is 11. So that is going to be the 11 multiplying by 3 on 11 plus 3. That is going to give us total of 33 on 14 ohms. That is for the Norton's resistance, because the series combination here is 11 and it is parallel to the 3 ohm resistor. Now we can also find our IN. Now when you look at the circuit, it will be very simple to use the superposition theorem as in the example 1, but because I use the superposition here, I'm going to use the nodal analysis so that you get varieties of approaches. Are we okay? So you can try your hands on using the superposition from the first example. So here I am using the nodal analysis. So the nodal analysis, this is what we are going to do. I'm going to, since I'm finding the current, let me take it out, the current. So this is going to be open circuited, although the terminal is there, and that is my IN for the nodal analysis. So the nodal analysis, how many nodes do we have here? I only have this node as my V1. Remember this part. We are not calling this part a node because it is assumed to be just a wire, continuous, because current is not going to split here. This part is not a node. A node is where current is going to what? Split itself. But here, because there is no elements at this part, current here, the same current is going to pass through this part. So our point is going to be at V1. Do you get my analysis? All right, so we have V1 over there. So that's our node. So that's at node 1. Here you can ground this whole part as my ground, and my V is going to be 0. So let me call this source is going to produce a current, say I1, and this current is going to be here. This is also going to be my I2. Are we okay? As my I2, because as I1 is entering the node, this is also entering. This must leave. So we can write the current equation that I1 plus the 7 is equal to what? I2. And now we can turn them into voltages. I1 is moving from a 100-volt source to the V1, and it is through the resistor 8 plus 7. I2 is also moving from when you look at here, I2 is moving from the voltage V1, and it will come back to the reference node because this part is not considered as our node. Are you okay? So that would be V1 minus 0 over the resistor, which is 3. Now, when you look at the resistor, it is passing through first resistor 3. The same current will come and pass through the second resistor 3. So how many resistors? 2. So 3 plus 3, making what? 6. Do we get that? So it is very complicated using the node analysis. You can go to the superposition, but once you understand this, that's why I'm taking my time. You are good to go. So now that we have this, we can express it and find a very good equation for this in terms of V1. When you simplify this, you are going to get a simple equation as 468 minus 7 V1. This is just mathematics. You can do that, equal to 0. So from here, my V1 is going to be 468 on 7, which implies that V1 is 66.86 volts. So the voltage at the first node is 66.86 volts. We are not done. We are going to perform voltage dividing. We are going to use the voltage divider approach because we know that. Let me cleanse some of them so that you get to see. Now we know that voltage, you have to apply everything you know. We know that voltage across this part is 66.6. Now that voltage is driving current through this 3 and through this 3. So there's going to be voltage dividing between them. Are you okay? And this is supposed to be simple, but we have to use the right way. If there is a voltage of 2 going to be shared between two equal resistors, 3 and 3, meaning each one is going to drop 1, this is going to drop 1. So that will be half of it. Are you okay? So meaning we can call this point as, let's call this point as a point A. So at A, because there is going to be a voltage drop at this 3 ohm resistor, then the voltage at A is going to be V at A, which is equal to half of the voltage, 66.86 over 2. And that is going to give us 33.43 volts. Are we okay? And now what do we know? We know that the voltage across the 3 ohm resistor is 33.46. It is also parallel to the voltage across the IN. And what do we know for parallel voltages? They are equal. So meaning voltage across the IN is equal to voltage across the A, which is equal to 33.43. Now we know the voltage. We also have to find the resistance. We know the total resistance in the circuit so that we can use that to find the IN. It is very simple. So let's look at that. Now we know the voltage across the IN, which is equal to 33.43. And we also saw that from the Norton's approach, we saw that the total resistance in the circuit was 33 on 14. Let me approximate it to 14.1. We can leave it in fraction form. Let's leave it in fraction form. So from here, then my IN by Ohm's law is going to give me 33.43 on 33 on 14. That is going to give me IN of 14.18 amperes. Please take your time, go through the video. So I'm going to have the effect of the IN being in parallel to the Norton's resistance, also being in parallel to the load resistance RL. So here, if this is coming, it is going to split into, let me call I1 and I2. So by the current divider approach, my I2 is going to be my Rn on, let me call this In, Rn plus RL times In. That is going to be 33 on 14. Everything divided by 33 on 14 plus the load, which is 6 times 14.18 amperes. And this current I2 is going to give me 3.999 amperes, approximately 4 amperes. So the current through the load resistor 6 ohm is 4 amperes. I hope you are going to get the same answer by using the superposition theorem. Thank you for watching this episode. If you don't understand anything, drop it in the comment section. Go through the video once again and you will understand. Thank you, subscribe and share the video.